Hello, everyone. Good morning. Thank you for being in this session about pattern matching. My name is Angelos Bimboudis. I'm working for the Java Platform Group at Oracle in Zurich. And today, we are going to talk about pattern matching from a little bit different perspective. We're going to see just we take a peek like under the hood, under the pattern matching engine, what happens. So this will help us take some decisions when we are working with pattern matching and our complex hierarchies, but also help us visualize a little bit about the future, which is very related to the work that we are doing. So I think this is the most dense slide I have, so don't worry. So pattern matching, the bigger picture. Okay, Java is full of features that abstract away details. Sometimes throw away details or just abstracting them. Like there are methods, for example, that return a general type, but from within the method you return a concrete object, so you abstract detail. Or you have an assignment and you are doing a widening reference conversion. You abstract away information. Or you put things into the components of a record, for example, or through the constructor of your class, essentially throwing away, storing details and hiding them. So all these forms are forms of abstraction, and pattern matching is asking the question that some operation that seems to be losing information, can I recover my data from it, or what was previously known on the other side of the use side? And pattern matching is a conditional a pattern is a conditional query. Just to give a very brief definition, that tests a match candidate for its shape. Okay, so this is now we are triggering the information retrieval about the shape of our data. It applies a test, instanceof. Everybody knows instanceof. We query about the runtime type that the JVM knows, so our program has more information at that point. And if the test succeeds, instanceof safeguards a conversion. Maybe a narrowing conversion. A narrowing conversion may, of a reference, for example, type, may fail with class cast exception. So safeguarding it with the instanceof, then the cast conversion will be safe. And then we can also, you see, like the next step now, we extract information through the components, let's say for a record, and then we can bind the results to local variables with names of our choice, because we have used the type pattern, for example, which is like point P. That P is the name of our choice, and then our algorithm can use it. And then success or failure is signaled appropriately through control flow and definite assignment, definitely unassigned variables, and all of these things. So if you have an if statement that uses the instanceof pattern matching operator, then inside the block you have all the information needed, all the variables initialized. Outside that, you don't. So I would like, so when we leave today here, I would like you to think that pattern matching is an engine, and it's actually a framework deeply rooted in the core, in the soul of the language, and its evolution will pay dividends in the future, because through this work, we are going to allow safe recovery not only from reference conversions, but also for primitives, because you can also cast away information there, and there, information is not hidden away in the JVM. Sometimes it gets destroyed when you cast like a value of a primitive type to another primitive type, so it makes sense to safeguard that as well. It will allow, evolving this framework will allow us to classify automatically in the future new types or new conversions when they appear. So you already heard me talking about safety, loss, and like all of these things. And we know from chapter 5 of the Java language specification all the implicit and explicit conversions that the Java language allows. Maybe in the future new types will appear or new conversions will appear. So these can be classified automatically. And finally, pattern matching is supported as a switch statement and expression, but also through the instance of pattern matching operator, aligning instance of with with pattern matching will also complete the slate and allow us to have a concise design for between instance of as a type comparison operator and pattern matching. So this is a first example. I have 2 slides just to show you a little bit what I meant. Object O equals hello. Okay, a widening reference conversion took place. String to object, always safe. The other way around, it's not always safe. So pattern matching helps us to recover the runtime type. Yes. From object to string, and then assign that to S. S has a precise type in my program, okay? So that I can invoke .length and do something specific. And this is with type patterns. String S, it's not by accident that it looks like a local variable definition. String S is called the type pattern, and it's the first form that pattern matching supports. And a little bit more convoluted example, imagine a declaration of a colored object that holds objects and colors, and then you see here that 2 widening reference conversions are happening. The new point is stored to a value of type object. If is passed to the constructor that has a value that has a type of object, and then the final new colored object is widened again in an object. And then with record patterns, we can recover both runtime types because that shape was out of interest for me. Or a colored object. I wanted the colored object of a point of a var x. I want to ignore y, and then of some color, I want to write. You understand. It's very intuitive. A brief now parenthesis that can spawn years of discussions is like such an analysis before could be either done with instance of like manually, okay, or with a visitor pattern, which I also like to discuss, because here is like some template that I thought that could do the same job as the previous snippet did, and I know that if I ask you now, like I will get 15 different, 20 different opinions about if this is exactly the same as before. The interesting things are that the hierarchy needs to be wired by the user. You see on the right-hand side an interface object that defines the accept method that accepts visitors. All variants, point and color object, need to implement that object. Then on the left-hand side, we see our analysis now nicely packaged together. This check condition implements the visitor. But now there are so many details that we can talk about. Apart from the boilerplate, like there's a lot of boilerplate to set up the hierarchy. This is not easily extensible. It is using double dispatch, so you cannot really invoke. You cannot pass the visitor like as to an object. It needs to be a colored object because of visitor likes to use all the static information available. Where is the traversal going? On the left side or on the right side? Which means, is it an internal visitor or an external visitor? Is it a functional visitor, like my accept methods return a value, or they are, it's an imperative visitor, like they are declared with void, like here. There are so many decisions here. So how can we integrate in the language a way that is more powerful, that is more convenient to use than a visitor? So the question is, what APIs support pattern matching currently? So Every reference type can be pattern matched, as I showed you before. But also, if we express our world with certain language constructs, then we can get the benefits of pattern matching. So with record classes, because record classes have a counterpart in pattern matching with record patterns, you get compounded and composed types, product types, as they are called, because it's like you pass, I don't know, one type as first argument, another type as another argument. So these are called product types because they can hold the cross product of all the combinations, theoretically. And the other kind is sum types, which are all about variants. And we all know the first variant. It's enums. It's a degenerate case. It's one value of several alternatives that we can enumerate, right? Which is very important. And then the second one is abstract sealed classes and sealed interfaces that we express one category of things, one variant of several alternatives. And now, by using those, pattern matching can give us more guarantees about our code, okay? And when we recompile our program, something can fail statically, as opposed to a visitor that you needed to go to the methods, change, add methods, to support a new variant. So we are going to talk about compile time and runtime properties of pattern matching. Pattern matching, as I said, is a framework of properties. The running example will be this one on the right. It has an animal, which is a sealed interface. It is subtyped by a bird, which is like a concrete final class, and mammal, which extends animal, and on its own has its two concrete subtypes. So here we have essentially one sealed hierarchy. It doesn't matter that it's one with interface and an abstract sealed class. I didn't include the code because it doesn't matter. We are going to go through the compile time checks, what applicability is, unconditionality, dominance, exhaustiveness, and the runtime behavior about safeguarding casting conversions. And we're going to talk a little bit about values that can flow through a switch, through our pattern matching, even though our switch is exhaustive. I will talk about what exhaustiveness is, but it's nice to set up a little bit the tone. Applicability. What does applicability mean? If the cast conversion can be checked and it is possible, so the compiler has verified that the conversion between two types is possible, then it can be safeguarded too. We see on the left-hand side two switches. The first one is correct because a mammal can be converted to a dog. Okay? And a mammal can be converted to a mammal, of course. Identity conversion, it's called. So, correct. The second one is not correct at all, the switch, because the first one is not the case bird. A mammal cannot be a bird, okay? So the compiler knows that, emits an error, that this case is wrong. So our whole switch is wrong. Applicability guarantees that you cannot accidentally guard a conversion that can never happen, which is an important property. And we already see that it delegates to the existing conversions between references. I didn't talk about primitives yet. And as a matter of fact, there are many cases that we can also see that witness this correspondence, okay? If you can cast something and the compiler says, yay, then this conversion can also be safeguarded. We see here a widening reference conversion. We see a narrowing reference conversion. We see that you can cast an object to an int array, which is another reifiable type, but you cannot cast a dog to a cat. So instanceof says incompatible types, and then the compiler in some cases, those called unchecked casts cannot verify if something wrong will happen, and these cannot be checked, so they were excluded from pattern matching as well. You get a warning on the cast. So this was one conversion that was excluded. The second property is called unconditionality. So here, we can define unconditionality that it is a compile time guarantee that the pattern will match every possible value that will flow through it, through the selector of the switch. So an unconditional pattern means that there is no possibility of a match failure to either of those cases. The first one got a mammal, like the previous example, right? And then it has a case mammal, so this is an unconditional pattern. It will match always. And the second includes the case animal as its last pattern, and every possible value is matched as well, okay? Since every mammal is also an animal using the widening reference conversion. So such conversion can also never fail. Similarly, it didn't fail in the assignment, in the very first example. So we're already gaining the intuition here that the widening reference conversion is always safe. In the pattern matching world, the pattern is unconditional for that selector. And the next one is called dominance, which is all about the detection of dead code. Patterns that can be never matched circumstantially because there is a preceding pattern that captures all of their values. Dominance ensures that all written cases are necessary. So I will read the switch, and all cases, if the switch compiles, are necessary, so they can capture something. So the first switch here matches a cat and then all mammals. So no case is covered by another one. And in the second case, we see that all cats are mammal. So this is a dead case. It can never be matched. So the compiler will say error, dominated by a preceding case label. And as a special case of this kind of dead code detection is that default, for example, is dominated when there is another pattern that can capture all its values. Here we matched over a selector of type mammal for the third switch, and we have an identity conversion. It's followed by a default. The default will never be matched. So one important now interesting data point here, that dominance is a relationship about two cases. So we examine here that one pattern, if one pattern is unconditional to the other one, then dominance will have, in a certain order, dominance will occur. So you already see that there is some certain form of delegation in the typing rules here. Like, if you have a relation about types and conditionality and patterns, and you can reason about something here, something else can reuse that as well. Dominance reuse this concept as well. And the last one is called exhaustiveness. And this ensures that all possible values are covered. Exhaustiveness. We see a switch that covers all possible values. Now, this is very connected with the SIL hierarchies that we talked about, because the compiler can now check if all variants are covered. If you have enums, it's going to be the same. If you have abstract shield classes and abstract interface and shield interfaces, the compiler can do the same level of reasoning. The first switch is correct because both variants are covered. The second is not because the bird is excluded from all animals. And what is important is that this works not at the top level of the pattern. A case dog is a top-level pattern because it follows immediately the case at the top level of the structure of the switch. But it can also, exhaustiveness kicks in at the nested level as well. And this guarantee is especially important when we do not have a case that matches everything. So, because as we will see a little bit later, maybe there are new cases that need to be captured here. But with all the compile time information that the compiler has at this stage, a well-typed switch that is also exhaustive means a lot. It's a very strong guarantee, because if we change something from our hierarchy and we recompile, we are going to get an exhaustiveness error on our use side, let's say. So let's switch gears a little bit and go towards runtime. And here is a sketch. This is not the compiler-generated code. The compiler-generated code uses bootstraps, and it has a more involved translation, but this captures the idea. Two switches, a top level on the left, a nested level on the right. And we see first instanceof. It safeguards a conversion that may throw a class cast exception. That corresponds to the first case, cut. M instance of cut, and then inside the if cut C equals a conversion that forces the cast. And the next case is, if you remember, an unconditional pattern. An unconditional pattern is so... the monitor is about to turn off. Can I... Thank you very much. So it's not so powerful that it doesn't need to be checked even. So this way it's on the else branch without any check. One last point is that if there was no way for a switch to capture its intent to match case null, the last case would match, right? Because instanceof would say, oh, this is null, so false, it would go to the unconditional pattern. However, a switch can state its opinion. So this is why you see this first line there. If m equals null, then throw null pointer exception. You can write in the switch at the top level case null to capture this intent. What I would like us to keep is that at the nested level, like this decision at the top level is not implied at the nested level, okay? So the nested level technically ignores null. And why does it ignore null? And now we are going towards the next point that I wanted to make. Let's talk about the reminder set. We have an exhaustive switch. The compiler said, yay, it exhausts all the universe of discourse of your domain. Everything is covered. What are the values that are excluded from there? It's null at the nested level, because at the top level, the switch has an opinion. So on the right-hand side, we say that the first switch is exhaustive even without null handling. And the reason is that if we had to handle null for every possible variant, we would need to do stuff like the switch below. We would, and like imagine if the compiler would tell you now that the switch is exhaustive because you handle null. With one case, it's not a problem. With one component is not a problem, but if you do for 3, you need, for example, your normal case, and then 7 cases, and then you would need to do that reasoning on your own. The second is what is a value, which is another value that is excluded from an exhaustive switch, is new variants of SIL hierarchies if you don't recompile the code. If you recompile, all the switches are going to fail. If you don't recompile the code, and you don't have a match-all case on your own, so that match-all case, either it is a default or an unconditional pattern, would capture also the new variants that were added later. We want a switch to be able to capture that as well. So when the user didn't add a default, the compiler adds a synthetic one, at least to catch this incompatible change from a separate compilation, this separate compilation issue. This can happen with enums and with SIL hierarchies. Yes, it ensures no runtime value can escape the switch without handling. So it is this feature, exhaustiveness. I would like us to think that it's not here to save us some from typing some characters, adding a default or an unconditional pattern. It is a very strong guarantee that we as users need to preserve for future-proofing our code. Relying on exhaustiveness on its own, it's very important. So let's step into primitives. So primitive conversions can happen in the language. We just talked about pattern matching. We just talked about pattern matching up until today, that it safeguards, or it is related only with 2 kinds of reference conversions: widening reference conversion and narrowing reference conversion. But there are so many more casts that can happen in the language. Not only among primitive types, but you can have chains of conversions as well. You can have unboxing, and then that is followed by something else. But let's keep it a little bit more tractable for now. We see here an integer, 1, 2, 3, 4, 5, and then a narrowing primitive conversion from int to byte. Okay? For the value 1, 2, 3, 4, 5. And the result is 57. And then when we convert back to an int, we get perfectly a number which is the numeric value of 57. But this is not what we started from. The value was completely destroyed. With reference types, this doesn't happen in the same way. You get some feedback, a class cast exception. Here, the value was destroyed from this narrowing primitive conversion. And why is the problem? Because many conversions like that you can use the modular arithmetic now and the range of bytes to realize that many conversions like that will end up in 57, so you cannot really go back. And okay. Narrowing primitive conversions are dangerous and potentially lossy. And we said that in widening reference conversions are always safe. Didn't we say that? That are always safe? The same does not happen with primitives. There are 3 pairs of types. The first one is int to float, that you can have loss of information on the widening part. So we took here, I've put here the first integer that is not exactly representable by a float. So when you cast that int I into a float, you get a float number. And then when you convert it back, you get a different number from that what you started from. So loss of information happens both ways here. That's very interesting. Okay, how can we, let's try to build up now from principles, like what we can do. How can we ensure the safety of primitive conversions manually? On the right-hand side, I show that we can do a range check to see if the one integral value lies in the range of the next one. And on the other hand, I have included a round-trip cast, but I excluded a value that when we reach that value, two approximations are happening and they are canceling each other out. So if I would leave the round-trip cast there without this exclusion, and somebody would convert integer.max value, it would, like, my algorithm would say, yay, you didn't lose information, and then later on you cast, but oh, I lost, why? So you need to carefully craft those tests to reason about loss of information. Another one, it's like a nice exercise, try to do the byte to car transformation. Then you see equals on the second if. So is it always equals? What kind of representation equivalence do we want? There are other methods. There are dot equals. There is double compared to. There are many details, because what happens with infinity? Then what happens with plus and minus 0? And some conversions consist of chains of conversions. So you would need maybe to think how to safeguard an integer to a float. An integer to a float, you can cast it. It's a valid cast conversion that first unboxes and then applies the widening primitive conversion. So observation, if we now pattern match over what we saw before from the translation, let's say, to what I'm showing here, we already have a mechanism to safeguard conversions among reference types. Pattern matching. Okay. With JEP 507, which is on the third preview today, and soon we are going to submit the fourth preview, we introduce primitive types in patterns, instanceof, and switch. And I would like us to think about this fact first, that it is a framework for the safety of conversions among all types. Keep this structure in mind, because when I change the slide, we are going to see something else. So please, remember carefully, like, the left column and the right column. The left column is about what JEP 507 developed as a framework to the very soul of Java around the safety of conversions among all types. An exact conversion will not lose information, like we saw with primitives, or throw an exception for the input value. Before I talked about an integer to a float. You may lose information after unboxing, right, into float, but the first can also lose information. You can lose the program pointer of your program, like when you have a null reference. So you can also safeguard, you should also safeguard that. An inexact conversion will lose information or throw an exception for the input value. So to reason about exactness, you need a runtime action now to check this. And the last one, the last definition, is about unconditionally exact. You don't even, there are some conversions that you don't even need to check the input value, just to reason about their safety. Already very related to unconditional patterns that we saw before. So on the right-hand side now, we see how JEP 507 plugged into this framework. We have applicability, and then applicability was saying if there is an applicable conversion among two reference types, but now it's among any type if a conversion is allowed. The second is called unconditionality, and we talked about widening reference conversion, but now widening reference conversion, I said it doesn't lose any information. Now we talked about conversions that can be unconditionally exact, so these two concepts can be unified. So unconditionality delegates to the definition of unconditionally exact conversions. Dominance continues to rely on unconditionality, a relation among two patterns. And exhaustiveness is null again for given, and Boolean selectors are exhaustive for true and false. So, like, see this, and now these are the changes, part of the changes, the main payload of the changes from the corresponding spec diff, the Java language specification diff file for this feature. We see on the left all the definition about what exhaustiveness means, what exactness means, the exact conversion, what loss of information is. A little bit below here is what unconditionally exact conversions are. And on the right-hand side, we see the properties of patterns that I discussed before. I didn't include exhaustiveness because it's in another place a little bit more wide. So we dropped restriction from applicability. The reference is crossed out. Now it works for everything. Before, primitive patterns like a primitive type of type T could also be matched by the same type T. So this is crossed out now because all conversions are allowed. And then unconditionality, it was all about subtyping. If you see the second paragraph, the first bullet of the second paragraph. So it was only about subtyping, but now we delegate to this unconditionally exact conversion. And dominance is unaffected yet. So this is now a summary. Here is a catalog of all the individual conversions that Java language supports. Plus, there are some chains of conversions, but these are very important for us now. Identity, mammal to mammal in the beginning. It's always safe. There's no safety check, of course. It's unconditionally exact. Widening primitive, mostly safe. So most of them are conditional exact, and there is a runtime check to figure out safety there for those that can be lossy. Narrowing primitive, there is a runtime check. Widening reference, it's unconditionally exact. Narrowing reference, there is a runtime check because failure may occur, and only the checked ones. And unboxing may fail, so runtime check, but boxing is also safe. Unconditionally exact. So this definition helps us tremendously already to reason about the safety of conversions. So allowing this reasoning in pattern matching allows us to reason about lossiness and recoverability of types of values in primitives as well. So if we have int I equals 1, 2, 3, 4, 5, like the first example, and we ask if I is instance of byte b, because there is an allowed conversion, so we can safeguard that, then the println is not executed. And if we have a sufficiently small int I, which means that it can't be represented by a byte, then pattern matching will kick in, the pattern will be matched, and then everything that you know already from pattern matching. Yes, the first conversion is not exact. The second conversion is exact. And now, if we do all this work to support all reifiable types in instanceof and complete the slate of all the allowed conversions in the universe of pattern matching, why not align instanceof with this reality? Because I didn't include it, but instanceof has always been defined in the Java language specification as the protector of class cast exception. It was always protecting a certain cast conversion. So with this proposal, instanceof can safeguard all conversions. So 2 more slides now that I will attempt to give a little bit a part of the vision for the future. Potential futures based on this JEP. Since we discovered that the method invocation allows widening primitive conversions, some of them can be lossy, 3 of them can be lossy, and assignment also can be lossy. Since we have now the tool, we can raise warnings for these occasions when the value on the right-hand side, as the first line shows, can realize that, oh, something can be here potentially lossy. So this is just informing the user. This is an idea. It can happen. When we have constant expressions, we have the value. So we know that for these 3 sublines, of the first bullet, we know that there is definitely loss of information is happening here. Of course, we cannot raise an error because this would be a huge change now, but we can raise a more informative warning here. Okay, that's one direction. Another thread is introducing constant patterns. Constant patterns can be another form of patterns integrated in the language. We have constants at the top level today, but they are not patterns. They are not adhering to the same properties of patterns. As a matter of fact, they are not adhering to cast conversions. They are adhering to assignment conversions. So introducing constant patterns would mean this feature plugs into the framework, talks about what applicability means, what unconditionality, can case person of one dominates other cases. And the translation could be based on primitive patterns, because if you have a box of 42L, then this could translate to semantically equivalent, let's say, to a box of long with a guard when the long is 42, I missed the L. And this could be a valid direction for us. And then continuing building on top of this is to introduce pattern assignments, which is a very much requested feature, which is the assertive way to deconstruct an object with a record pattern. You have a record pattern, here person of string name int age equals and my variable. And this can be semantically equivalent with an exhaustive switch with one case. Because if this compiles, it needs to correspond to a switch with one case. So exhaustiveness plays a huge role here. And then the last part is to align with Valhalla, because Valhalla, and now we are circling back to the first slide when I talked about new conversion. So if we talked about instanceof that can safeguard all existing conversions, and Valhalla may introduce new kinds of conversions, it needs to also plug into this framework. And as a matter of fact, I can show the next slide, the last slide. Let me start from the from the right-hand side for the absolute future, because now I think it's very exciting. Allowing custom conversions to flow through the framework and reusing all this machinery. What is safety of conversion? Is this convertible? Querying the compiler if there is a conversion through instanceof. Running a conversion through instanceof, the pattern matching operator and the switch as pattern matching. And allowing all that to work with custom conversions for float 16 and, I don't know, user-defined value classes. This is a very important property. So Project Amber, in the beginning, introduced switch expressions, pattern matching, for instance, of sealed classes, then pattern matching for switch, record patterns, unnamed patterns recently. We are here now with primitive patterns. This is a proposal to introduce primitive patterns. Captures the whole idea around the safety of conversions, and the three ideas, potential futures that I showed you in the previous slide are the second to last here. We talked about custom conversions, but another big effort that we are doing is allowing normal classes to be deconstructed, not only records which have implicitly a way to be deconstructed with record patterns, which is embedded in the language, hardwired in the language. Another effort is to allow normal classes to be deconstructed, and that you can recover information through normal classes, for normal classes through pattern matching, which is very important in the way that we are constructing our APIs for pattern matching. So thank you very much. I hope we got the idea about pattern matching being as a framework around conversions and safety and loss, making Java even more safe language for the users. And yeah, if you have any questions, we can take a few here. So we have 2 minutes. We may have time for one question, or at the booth later, you can find me. Thank you very much. Yes? Excellent question. So, excellent question. So the question was for deconstruction for normal classes. Do we get to deconstruct only, to return back only public fields, or rely on existing getters, similarly to the accessors that record patterns are doing? So in the first prototype, we introduced a new form of declaration called deconstructors that could query the internals completely and then return, essentially initialize. I would need to show you now. It would look like a method, like pattern point int x comma int y, and inside the method you would write match point 1, 2 if the pattern would match. A deconstructor could always match, so you would return like the values. Let's say they are hardwired, 1, 2. With this approach, you could also discover the truth from within the object. But another possible solution is what you said. Allow the user to write the accessors or existing accessors and then wire them through another kind of pattern matching mechanism. So we are still discussing about that. That was a very good question. Thanks.
You wouldn't use reflection then, I guess?
No reflection. Yes. Okay. Thank you very much, and thank you for coming.